Speakers are on a 20-minute schedule this morning. Our first paper, 71A, is entitled Aldol Condensation and Ketone Formation on Alkali Metal Zeolites. The authors of this paper are Professor Rhoday, Paul E. G., and Linda N. Marquez. Our speaker will be Professor Rhoday. He's Associate Professor at San Jose State University, Chemical Engineering Department. He received a BS degree in Chemical Engineering from the University of Kentucky and his PhD at BPI. Will you join me in welcoming Professor Rhoday?
If I go without a mic, can everyone hear me fine? I want to recognize, first of all, the people who have cooperated with me. Paul G., who is a graduate student and I graduated this fall with his master's degree and has moved on to the University of California at Los Angeles to get his doctorate. And Linda Marquez is a senior this year and finishing up and going on to UC Berkeley. We've been working on the project for about the last 2 years. We're talking based mostly from Paul's work on his master's thesis. When we started the work several years ago, we were interested primarily in trying to remedy a discrepancy in the literature. Primarily in the early 70s, Isakov of the Soviet Union had done some studies in which he had reacted in butyraldehyde with over alkali metal zeolites, sodium Y, acid form HY, and potassium Y, and found that he was able to get Aldol condensation reactions. And he felt that his catalysis was primarily the basic nature rather than the acidic nature that people normally associate with zeolite catalysis. So some work that I had done at Virginia Tech about 4 or 5 years ago, we had observed that with the same type of reactions, or same type of reaction feeds in butyraldehyde, that we were able to go to ketone formation, and ketone formation primarily being from C7 ketones, diisopropylketone N and isopropylketone, and di-N-propylketone. We had done those studies in propylene hydroformylation atmospheres, and on rhodium sodium Y zeolites. Sodium Y then would be, in comparison to Isakov's paper, a more acidic catalyst than, say, potassium Y. So we were wanting to go after the acid-base character of the zeolites and how it reacts with the aldehydes. So with that, I'd like to say that our objectives were twofold. One is that we wanted to investigate the formation of ketones from aldehydes as a function of acid-base character of the zeolite materials, and also take a look at the acid-base character of the alkali metal zeolites by aldol condensation of N-butyraldehyde to 2-ethyl-2-hexanal. Just in case some people here haven't reviewed their organic chemistry text recently, aldol condensation is both acid and base catalyzed in homogeneous by homogeneous catalysis. Here I have initially shown the acid-catalyzed aldol condensation for homogeneous catalysis. You see that you have the formation of the attack of the acid at the carbonyl oxygen, and that protonated carbonyl group reacts with the enol group here to form the aldol product. In the case of N-butyraldehyde, the R groups would be both ethyl groups, so we would have the dehydration of the aldol product to form the enal. The 2-ethyl-2-hexanal is commercially important and used eventually by hydrogenation of the enal product to the alcohol, and that alcohol is gone on to produce plasticizers in a very large commercial process. For the base catalyzed reaction, you have formation of a carbanion the alpha carbon of the carbonyl group. That attacks the carbonyl carbon to produce the same aldol as shown on the previous slide. That aldol is then dehydrated to produce the same enal group. When you compare the acid versus base catalyzed reaction, it's generally thought from a homogeneous standpoint that the route and energy levels to get to this product are basically the same for acid and base catalyzed mechanisms. However, the dehydration to the enal product is a lower activation energy process for the acid catalyzed version. And we want to keep that in mind for some later results. So today I'd like to present some of the reactivity results for our reactions of aldehydes over alkali metal zeolites. We had formed our studies in a differential reactor system. We have 4 mass flow controllers, so we can take a look at propylene hydroformylation conditions along with the helium diluent or n-butyraldehyde, which is fed by a syringe pump to a vaporizer to a differential reactor in which we operated. We operate the reactor at basically 1 atmosphere and 150 degrees, 150, 200 degrees Celsius. Our product analysis is done by online GC and capillary GC, so we can get good resolution of our products. I'll keep it pointed up. The catalysts that we used were the
You got to step out of the way of the light.
I'm sorry.
The catalysts that we used were 3 alpha metal zeolites, cesium, that should be an S here, cesium, sodium Y, lithium, sodium Y, and sodium Y. We used from PQ Corporation sodium Y zeolite, which was just washed in distilled water, or the cesium and lithium were prepared by ion exchange of the sodium Y zeolite in a 0.2 normal chloride salt solution. Our final products were about 80% cesium and 70% lithium, respectively. We also used non-zeolite materials. We used Aldol alumina and magnesium oxide to give us both an acidic and a basic catalyst for comparison to the alpha metal zeolites. We looked at the reactivity of really 3 different groups initially. We were wanting to reproduce some of the propylene hydroformylation results, or propylene hydroformylation environment results from BPI, and found that for a propylene, hydrogen, and CO mixture, that for all 3 or all 5 of the catalysts, we had initially hexenes to start up with, and they eventually died out to 0 activity. Magnesium oxide was not active for hexene formation. Yet you remove the hydrogen and carbon monoxide, you found that the only thing important for the hexene formation was the olefin, the propylene. If you take a look at reactivity of isobutyraldehyde, it was not reactive in any case on the 5 catalyst. Aldol condensation catalysis to 2-ethyl-2-hexanal was stable on all 5 of the catalysts at varying degrees. I'm going to present the relative values later. Initially, we found, though, that we had some difficulty in preparing some stable aldol condensation catalysts. Primarily, if we just heated the catalyst to 150 degrees in a helium stream and began an n-butyraldehyde in helium flow, we had an activity, but it decayed to 0. If we, however, absorbed propylene prior to our introduction of n-butyraldehyde, we were able to produce a stable hydroformylation catalyst. For the cesium sodium Y, our rates were about 2 times 10 minus 4 moles per gram per hour, and was a stable catalyst. The role of the propylene, we believe, is simply to block some of the acid sites for the catalysis, so that for the reactivity of other aldehydes and the aldol condensation products to produce larger materials within the zeolite pore that would eventually block the activity for aldol condensation. So we've done some temperature programmed absorption studies in which we have seen propylene adsorbed at much higher, or desorbing at much higher temperatures than any of our aldol condensation products or n-butyraldehyde, so that it does stay around at a significant level and does participate in blocking the catalyst rather than just consumption, say, of peroxide acid sites. I have to go with a multi-visual presentation this morning because there's some mix-up in the I'm getting my slides back. I want to present the reactivity as a function of acid and base character for our 5 different catalysts. And we looked at the acid-base character by looking at isopropanol decomposition. Acid catalyzed decomposition of isopropanol goes to propylene, base catalyzed goes to acetone. So if you can take a look at the relative rates of formation for those 2 products, you get an indication of the relative amount of acidity and basicity. The aldol condensation rates are listed here on the right, and if you take a look at the relative rates that we have, our best catalyst is the cesium sodium Y, followed by sodium Y, followed then by lithium, alumina, and then magnesium. If you try to correlate with the acid and base character, you see that for the most acidic catalyst, it's not our highest aldol condensation catalyst. If you go with our strongest base, however, or if you really consider these as basically the same value, that our strongest base is our best aldol condensation catalyst. If you think back to the mechanisms that I pointed out before, acid and base catalyzed conversion of n-butyraldehyde to 2-ethyl-2-X and now, it doesn't quite jive to say that just one is acid catalysis and another is simply base catalysis. And I believe we have enough evidence to say that for cesium sodium Y that we actually have both the acid and the basic sites taking part in the reaction. Initially the basic sites being able to conduct the aldol condensation reaction, or the aldol reaction, and then the dehydration step, the lower activation energy step from a homogeneous standpoint is done by the acid catalysis. In support of that also is some results in which we taking a look at absorbing acidic and basic gases. Looking at absorption of ammonia and absorption of CO2, you see for cesium sodium Y, for either by just simply pre-treating the catalyst and then exposing it to n-butyraldehyde, taking a relative rate to our steady state value, you see we have a reduction in our steady state value. For pre-treatment of CO2, we have a similar type of reduction by about 1/3. If we simply pulse the ammonia or pulse the CO2 onto the catalyst, we get like or similar type of reductions in activity. One of the things that I'm not too sure about, and I present here, and maybe some people have some ideas, is if you look at magnesium oxide and the same types of pre-treatments, that uniformly you get increases in activity. And I'm not very sure about exactly why that is, other than maybe for ammonia you're producing more acid sites in its absorption, or CO2 you're cleaning the surface and initially desorbing product off the surface. So that, and compared to the reactivity or the relative values of acidity and basicity, we think that both sites are taking place in the aldol condensation reaction. I mentioned some things about ketone formation and what we had observed at BPI. So in this slide, in conditions, I show the conditions in which we've been able to produce C7 ketones. Primarily, I have the isobutyraldehyde or N-butyraldehyde reactivity that I've shown on the previous two slides. You see that isobutyraldehyde as a pure feed does not react to form any aldol condensation or ketones. If you go with an N to I ratio in the feed of 1, N to I ratio of 4, and take a look at the cesium sodium Y column, you see that we do not have any aldol condensation, but we have iso N-propyl ketone, di-N-propyl ketone, and quite a bit of propanol also. For N to I ratio, our aldol condensation, N to I ratio of 4, our aldol condensation rate does come back. It's not back to the same levels as we had previously with just N-butyraldehyde as the feed. You have more propanol than N to I 1. You have basically the same rate for iso and N-propyl ketone, but you have 4 times the rate, 4 times the ratio for di-N-propyl ketone formation. So in comparing our results with Isaac's paper, I think it points out to a couple of differences. One is that he had N-butyraldehyde at 200 degrees in the liquid phase with the solid zeolite and no isobutyraldehyde around. In the vapor phase, at a lower temperature with isobutyraldehyde present, we do get the C7 ketone formation. It doesn't quite explain why you get the ketones, but it does explain some of the discrepancies from the literature in our observations. For magnesium, you see basically the same types of results. You see just propanol initially for N to I of 1. Aldol condensation comes back at about N to I of 4, but it dies out eventually, and you have di-N-propyl ketone being formed over that catalyst. So in conclusion, I want to make a few points. One is that the propylene pretreatment is required in order to produce a stable aldol condensation catalyst, and we feel that the primary mechanism for that is that it blocks the higher strength acid sites that cause further reactions of the aldehydes. We do not see any cross-aldol condensation products. However, we do see the C7 ketones. Cross-aldol condensation is a problem if you have mixed aldehyde streams reacting with catalysts. For iso and N-butyraldehyde aldol condensation reactions, you should be able to produce 4 different products. But that does not occur at all. We just are able to see the 2-ethyl-2-hexanal or the aldol condensation of N-butyraldehyde. We see that over the alkali metal zeolites and also on alumina and on magnesium. Aldol condensation, we think also for the alkali metal zeolites is a 2-step process, both acid and base catalyzed. And finally, the C7 ketone formation is not quite understood, but it is shown to be a function of N to I ratio in the feed. Finally, I want to recognize the National Science Foundation for support of this project. Thank you. I'd like to answer any questions you might have.
Paper 71B, title is an isothermal fixed bed reactor with non